So let's look at deadlock. Let's look, for example, we're in CPU 0 and we're doing a rename. Okay, so we're renaming. We're renaming A/F to B/F. And on CPU 1, we're renaming B/J to A/J. So how might these work? Well, we need to be working with these two directories, A and B, and so we need to acquire some locks on them. So CPU 0 just acquires them in order. So it's going to first acquire a lock for A, acquire a lock for B, and then when it's done, release them in the opposite order. Well, if CPU 1 does the same sort of thing, it acquires first the first lock, so for B and then for A, then we've got an issue, right? Our issue is, what if CPU 0 acquires a lock for A, CPU 1 acquires a lock for B, and then CPU 0 tries to acquire the lock for B, and CPU 1 tries to acquire the lock for A. Then they'll both be in this, what is sometimes called a deadly embrace, right? 0 holds A waiting for B, B holds B waiting for A. Neither of them are ever going to get it. So this could end up in a very bad situation, right? And this is deadlock. So there are a variety of ways to try and deal with this, either to determine the deadlock has happened, and then what do? You're going to just kill one of these processes or one of these threads, right? Or, so really, there's a set of circumstances that can cause deadlock, right? One problem is if you hold on to a lock while you're trying to acquire other locks. So one way to deal with it is you just acquire all the locks you need at once. Here, CPU 0 acquires A and B, CPU 1 acquires A and B. One of them is going to get both A and B. The problem is that sometimes you don't know exactly what locks you're going to need. A second is the fact that once you have a lock, you can't get it kicked off. So if for somehow we could notify CPU 0 that it's losing lock A, then CPU 1 could go about it to its business, and then CPU 0 could somehow try and reacquire a lock A. One way to deal with this is ensure that all of the threads try and acquire the locks in the same order. Right, if we do it in the same order, then if CPU 0 tries to acquire A and B in that order, and CPU 1 tries to acquire A and B in that order, then whichever one gets A first is going to be able to continue. And then the other one will have to wait for them to go through to the end of their critical section and release A. So that can work. You have to determine kind of what an order means. One possibility might be, for instance, the virtual address of the lock. Okay, we know that provides some ordering. It can be complicated. Avoiding deadlock, unfortunately, can be a complicated problem. Sometimes also, it's hard, locks can tend to break abstraction, right? Because it's hard to know which locks are acquired by each module, let's say. So you call a function, and you might need to know what locks it's trying to acquire. You also may need to know what locks possibly you are required to already hold in order to call a function. So it can be difficult. Locks can be quite a bit of pain in the ass. One possibility to avoid locks is, to the extent that you can use immutable data structures or immutable values, you don't have this issue because of the fact that we're never going to have two processes trying to write to the same value. So that is one possibility that can help. So some languages, in fact, promote that. Erlang is a good example where you have immutable values, and so you really don't have this locking. Go is also another example where the way you run these Go routines is communicating via channels rather than trying to communicate via shared variables. So we try not to have shared variables, which lead to these locking and concurrency problems. And instead, if we communicate among channels, then we don't have this locking issue.